In this letter, we present InLiER, learning-free heterogeneous LiDAR place recognition via intermediate mixed-radix structural keypoint tokenization. This work addresses a critical challenge. How do we perform robust place recognition when robotic platforms combine LiDARs with fundamentally different sensor characteristics? Modern platforms increasingly combine heterogeneous LiDARs, from 128-channel 360-degree spinners like the Ouster to 6-channel 70-degree solid-state units like the Luvox Avia. Same location, radically different scans. This heterogeneity exposes two critical failure modes. First, FOV asymmetry. Descriptors built on fixed polar grids treat unobserved directions as geometric emptiness. Over 80% of a typical descriptor is actually vacant under a 70-degree field of view. Second, density variation. The same surface yields only a handful of points on a 16-channel sensor versus dozens on a 128-channel device. Density-dependent descriptors conflate this sampling difference with true geometric differences, breaking feature matching entirely. The root cause is shared. Existing methods build descriptors directly on raw points, coupling place description to sensor characteristics rather than to scene content. InLiER breaks this coupling with an intermediate representation. Height-sliced keypoints from structural elements, each assigned a mixed-radix token ID encoding height, radial distance, local shape class, and azimuth, all in a compact sub-2 kb representation. The same token set is then reorganized across three stages. First, MINT, minimum ceiling intersection, performs rotation-invariant shortlisting with pairwise height ceiling pruning. This ensures sensors with mismatched vertical fields of view are compared only on their common vertical support. Next, BEAM, binary elevation azimuth matching, reincorporates azimuth information and recovers a coarse yaw estimate through binary bitmask alignment. The height occupancy at each radial azimuth location is encoded as a bitmask, and we perform exhaustive circular shift scoring using only bitwise operations, making it extremely efficient. Finally, the top candidates proceed to token-guided geometric verification. We establish correspondences on spatial indices, apply ransack to the XY plane, recover the in-plane transform via SVD, and estimate the vertical offset independently. This yields full 6 degree of freedom pose recovery without touching the raw point cloud. The key insight: one shared intermediate representation, 4 distinct uses: retrieval, yaw estimation, verification, and pose, with no retraining and no separate modules. We validate InLiER in real-world field experiments on a ClearPath Warthog UGV across a campus dataset with 2 to 2.7 kilometer sessions. The database uses an Ouster OS032, a 32-channel spinning sensor with 360 by 90 degree field of view. Queries come from a Seond Robin W, a semi-solid state sensor with 192 scan lines, 120 by 70 degrees, and extreme point density discrepancy. This is a genuinely challenging cross-modal pairing with FOV asymmetry, different scanning modalities, and dramatic resolution mismatch. Despite these obstacles, InLiER achieves 400 true positive loop closures and only 4 false positives. The token representation remains compact, less than 1 kilobyte per query submap, suitable for bandwidth-constrained multi-agent deployments. The few false positives are localized to self-similar plane wall geometry, a clear and identifiable limitation. Let's now see this in action. Here's the live campus field experiment. At the bottom, gray points form the Ouster database. Its blue trajectory shows the recorded path. Above it, the orange trajectory represent the queries from Robin W, and orange key points appear in the upper map as well. The algorithm evaluates each query frame against the entire database in real time. When a true positive loop closure is detected, a green edge appears, connecting the query keyframe to its matched database keyframe. Blue points show the corresponding database keypoints that aligned with the query. At the upper right panel, you see a closer view. When a true positive triggers, the detected database submap is transformed to the query frame using the estimated 6 DOF pose, shown as green points. Not every detection is correct. You'll notice 4 red edges, false positives. These occur in the plane wall region of the campus where geometry repeats and the algorithm incorrectly matches structurally similar but spatially distant locations. At the lower right, you see the MINT and BEAM descriptors for each matched pair. The histogram shows the rotation-invariant range shape distribution after height ceiling pruning, Notice how both database and query histograms are truncated at the same height ceiling, handling FOV mismatch implicitly. The binary bitmask below shows the beam encoding, height occupancy at each radial azimuth cell. This is what enables yaw estimation via bitwise alignment.